Okay, so in our 11th lecture here, we're going to double back and look at infinite series again in a more sustained manner now that we've talked more generally about sequences and the Koshi Criterion. So basically, we'll prove some of the more common properties of series that you probably saw in calculus, and we'll cover at least one property that you probably didn't. And that'll be it for the material in Chapter 2. So this will take us up to the point of the first exam. So the first thing to look at is just some basic property of series. And it just comes from translating a theorem about sequences directly into series language and notation. So we know we have a theorem that says that if we have a sequence converging to some number, then that implies that if we take that sequence and we multiply each term of the sequence by a fixed constant, then the resulting sequence still converges, and it converges to what you would obviously think, just that same constant times the limit. So if we have a series, then we can look at the sequence of partial sums, right? So if we have the sequence of partial sums, okay, so this S sub m is the sum of an, say, from n equals 1 to m, and let's say that's converging to some infinite sum, S, infinite sum in quotes. Then if we just take this theorem here and plug it in. So what this should say is that C times the partial sums, that's going to converge to C times S. And what is this C times the partial sums? Well, that's C times the sum from n equals 1 to m, an, right? But this is just a finite sum, so we can, of course, distribute that C over the sum. So this is just the sum from n equals 1 to m of CAN, right? And what is this CS? Well, that S, normally we would write that as the sum from n equals 1 to infinity of an, right? And so here we have these partial sums here, right? This is a partial sum here, approaching this thing, right? And as m goes to infinity here, right, we would write just m equals infinity on the top there. So that implies what we have is that n equals 1 to infinity of CAN equals C times the sum from n equals 1 to infinity of AN. Right, so we're just taking this property of sequences, and we're just taking a particular kind of sequence, the sequence of partial sums, and then just seeing what that yields for us. And so what this tells us is that infinite sums, right, these infinite series, have the property that you can pull a constant out of this infinite summation. Okay, so constants distribute across infinite summation. So that would be sort of the first property that we get from just our general study of sequences in general for series. And a similar one would come from the other property of summation, right? So if we take two series, so if we have AN approaching A, we have BN converging to B, then we know that implies that the sum of the two, right? So if we form a new sequence by making the nth term of our new sequence equal to the sum of the nth terms of each of our given sequences, then that converges to the sum of the limits. Okay, so the limit of the sum is the sum of the limits. And if we take these to be partial sums, so if we have SM converging to S, and SM is the sum of AN from n equals 1 to m, and then we have TM converging to T, and TM is equal to the sum from n equals 1 to m of Bn. Okay, so we have two different series here. Then that must imply that SM plus TM, that converges to S plus T. And what is SM plus TM? Well, that's just, right, just plug it in. And we have this finite sum, these two finite sums. But of course, when we're talking about a finite sum, we can rearrange our finite sum, right? So this is just going to be, so this sort of strictly says take the, sum the a's first and then sum the b's and then sum those two together. But we can do that in any order. So we can do the sum of the first first a and the first b, and then the second a and the second b, and then sum all of that stuff together, right? Which is exactly what we're doing when we rewrite this way. And so what we're saying here is that this partial sum now must converge to this same, to this s plus t. And so what that means is so this thing converging means we replace the m with infinity up there. And so we get n equals 1 to infinity of an plus bn. That must be equal to s plus t. And so that's the sum from n equals 1 to infinity of an, that was our s, and the sum from n equals 1 to infinity of bn. So essentially, if we have two different convergent sequences, two different convergent series, we can sort of rearrange the order in which we do the sum, right? Because this sort of says sum all of the a's, quote unquote, sum all of the a's first, and then sum all the b's, and then add them together. This says what you can do instead is sort of rearrange and take those, the first a and the first b, add them, second a and the second b, add them, and then add all of that stuff up, right? So it's a very different order of summation, and in either way you get the same result if you start with convergent, two infinite series which converge. Okay, so that I'll just sum that up in the following theorem. Okay, so this is the theorem that comes out of it. So this is just a summary of what we just discussed. You can pull a constant out of an infinite sum or push it into an infinite sum, and you can sort of distribute the infinite sum over two different sums here. Okay, so this infinite sum sort of distributes over infinite summation in some sense. Okay, so the next direct translation we'll make from sequence language to series language is the Koshi Criterion. So remember, the Koshi Criterion says that a sequence converges if and only if it's a Koshi sequence. So in terms of, if I take our sequence to be a sequence of partial sums, I have a sequence of partial sums is converging if and only if that sequence of partial sums is Koshi. And so we can just, we'll try to write that down. So remember, so the structure of the being a Koshi sequence. So remember, to be a Koshi sequence, it must be that for all epsilon, and I'll just use shorthand here, logical shorthand, for all epsilon greater than 0, there has to be a point in the sequence, right? So some capital N, such that when m and n are bigger than or equal to n, then it must be the case that that implies that a sub m minus a sub n is less than epsilon, right? So once you go out far enough past this point in the sequence, the terms of the sequence are very close to each other, right? Getting sort of arbitrarily close to each other. And so now we want to apply this to sequences, right? So to sequences of partial sums, right? To series. So we take our sequence to be a sequence of partial sums. And so if here we take this to be, say, s sub m and s sub n, right? Let's see, this s sub m, so let's say we're summing a sub, and I'm already using m and n, so I guess I'm going to use k here to index the sum. So k equals 1 to m, and then minus the sum k from 1 to n of ak. And so I'm sort of looking at this. And what is this? Well, this is, so the first sum there, that is a1 plus a2 plus dot 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 up through am. And then we have a1 plus a2 plus dot 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 an, right? And so you can see you're going to get a lot of cancellation here. And so a1, that's going to cancel a2, that's going to cancel. And basically what's going to happen is, whatever between m and n, let's say if m is bigger, right, then if m is bigger than n, then an is in here somewhere, and that's sort of all going to get canceled out, right? So at some point in here, you're going to have, so let's see, so we can sort of rewrite this then, I guess. So let me just give myself a little bit more room here. So you have plus dot 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 plus an plus, right, and then we can continue on to am, and we would get this big cancellation like this, and we would just have the sum from, well, the an one canceled out, and so we would start our sum from k equals n plus 1 up to m, right? And of course we have absolute values around this. And so this is if m is bigger than n, right? And I mean, but this isn't really an essential restriction because this this difference here, this am minus an or sm minus sn, it's because it's in this absolute value. We can interchange m and n, right? So you can just sort of, you know, if m is the one that's smaller, you could just sort of relabel things. You can just relabel the m and the n so that now with your new labels, the m is the bigger one. Okay, so this distinction between m and n is not really essential. So sort of without loss of generality here, right? Between these m and n, one of them is going to be the bigger one, and you can just let m be that bigger one. Right, and m equals n, you always have this difference being equal to 0. That's already trivially less than 0. So what we can do in this definition here for Cauchy sequence, we can just say that our little n is bigger than or equal to n, and our m is bigger than n. Okay, so that'll just be a slight, it's on the surface looks like a different definition, but it's actually content-wise, conceptually, the exact same definition. Okay, so if we use that as our definition for Cauchy sequence, then this difference in partial sums just becomes this sum. Right, so when your m is bigger than n, all of those first n terms in your sum gets canceled out when you do this difference, and so you're just starting at n plus 1 going up to m. That the sum of those terms has to be less than epsilon. Okay, so if we just take this that we've written down here, we can write this definition, or sorry, write this theorem of the Koshi criterion in terms of partial sums. Okay, so this is what the Koshi criterion then looks like for series. So a series converges if and only if the sequence of partial sums is a Cauchy sequence. That means for all epsilon greater than 0, there's a point big N at which, once we look at the partial sums that are past that point n, the difference in those partial sums is less than epsilon. Okay, and we just discussed how the difference in those partial sums, as long as your m is bigger than n, you're just adding the terms after the point little n up to the point big M, right? So you sort of have, basically this criterion is saying your sequence, your series converges when there's some point after which, no matter how many terms you're summing past that point, right? So there's this point big N such that when you start just past that at n plus 1, no matter how many terms you sum after that, right, up to this arbitrary m here, this m can be totally arbitrary, you sum all of those terms, their absolute value is less than epsilon. Okay, so it sort of says the tail, the sum of the tail is arbitrarily small. And one immediate corollary of this is something that's you might recall from calculus, which is that if a series converges, then the terms in the series that you're adding up in the series, they have to be going to 0. Okay, and of course the converse of this is false, right? Just because you have the terms of a series going to 0, that doesn't mean the series converges, right? The harmonic series being the standard example. So this diverges even though the terms 1 over n are going to 0. But this says the converse, that if the sequence is converging, then the terms must be going to zero. Okay, it doesn't say the terms going to zero implies convergence. It's the other way around. Okay, so any convergent series, the terms must be getting smaller and smaller, going to zero. And the reason for that comes directly out of this Koshi criterion. There's other ways to prove it, but it's just an immediate corollary of this Koshi criterion, because what you can do is, right, these m and n are totally arbitrary here. So what you can do is you can take your m equal to n plus 1, right, little n plus 1, and then this is just a sum of one term, right? If m is little n plus 1, this sum here just becomes, right, so if you take m equal to n plus 1, then this sum here, just becomes just the term a sub n plus 1. And so it says that this term must be less than epsilon, right? And we can do this for any n plus 1 after this capital N. All of those terms by this argument must be less than epsilon, right? So that's saying that all of these a's are arbitrarily small after some point, which exactly just says that the sequence of terms themselves are going to zero. Okay, so you get this immediate corollary by taking m equal n plus 1 in this Koshi criterion. Okay, so this is the corollary. If your series converges, then the sequence goes to zero. And the proof is to take m equal to little n plus 1 in the Koshi criterion above. So I know that's missing some details. You should be able to prove them to fill them in. So this would be a good exercise before the exam to fill in the details here for yourself. So we take this in the Koshi criterion above. Okay, so a true proof would say let epsilon greater than 0 be given, and then choose your capital N appropriately, and that should be you should be able to extract all of that just from this sort of little hint here. And this is your last note, that the converse is false. Just because the terms go to 0 doesn't mean that the sequence converges. Just think about the harmonic series. The next immediate consequence of this Koshi criterion is the comparison test for series from calculus. That if you have sequences such that the A sequence is less than or equal to the B sequence, at least after some point, okay, so we really only care that this occurs eventually, then if the B sequence sum, right, the sum over the B sequence converges, so we create the series from using the B sequence as terms, if that converges, then the A one also converges. And the basic idea is that if you're adding up all of these terms and that one's converging, then that sort of puts a kind of upper bound on the A's, right? So you're summing up all of these positive B terms, and that's coming to a halt, right? You're coming to some sum, but those are sort of suppressing the sum of the A's, right? The sum of the A's can't exceed that sum of the B's on the tail end. So the sum of the A's has to be coming to a halt too. It can't be getting arbitrarily large, and then sort of by similar logic, if the A sum is diverging, right, then that means adding more and more terms of these A's is getting sort of larger and larger, but that must be pushing the B's sum from below to diverge. And this is indeed the case, as follows from the Koshi criterion for series. So let's carefully prove this one just to make sure we are knowing how this Koshi criterion is working for series. So part 1 here, we have to show that a series converges. We're going to use the Koshi criterion, so we need to let epsilon greater than 0 be given. So let epsilon greater than 0 be given. So we want to look at so we want to sort of bound the absolute value of the sum of the AKs from k equals n plus 1 to m, right? Sort of a tail sum, a partial tail sum of this series. We want to bound that by epsilon. And of course, the a's, right? So the point is that the b such sums, right? So the b sum, because we know that converges by the Koshi criterion, we should be able to, after some point, be able to make these b's less than epsilon, right? And of course, the a's are less than the b's, so we should just be able to say that this is less than or equal to, right? And I mean, in fact, these a's are greater than or equal to 0, but what we have to be mindful of is that we're assuming this only after some point, right? So sort of eventually this should happen. So we should be able to just sort of take away these annoying absolute values here and just say this, as long as the n plus 1, right? So we need this n plus 1 and m, right, to be bigger than or equal to this point n in the sequence. In our indices. So we just have to take account of that in the proof. And so the other thing we need is so we have this n here. We need our n plus 1 and our m to be at least that far out. And we also need our n plus 1 and m. We need them to be far enough out that we can apply the Koshi criterion for b. Right, so in the b sequence, we're going to be given some n1 such that when our m is bigger than or equal to n1, then we can apply this. All right, so basically, we kind of just want our n and our m to be bigger than or equal to the max of these two things. So that's going to be the basic structure of the proof. So we let epsilon greater than 0 be given because of the convergence of the B series. So since this converges, and by the Koshi criterion, there is an n1 such that when m is bigger than little n is bigger than or equal to n1, we have that the sum from n plus 1 to m, so this partial tail sum of the b's, is less than epsilon. So choose n2 to be the max of n1 and n. Okay, so what we're going to want to be able to apply this inequality here, and also apply these inequalities there. Then if m is bigger than little n is bigger than or equal to n2, let me get rid of this. It follows that the sum of the a's, so the partial a tail, so k from n plus 1 to m, the absolute value of that, well, each of these terms now is greater than or equal to 0, right? Because k is between n plus 1 and m, that's bigger than or equal to this n2, which is bigger than or equal to n. Right, so we can apply positivity of the terms to get rid of that absolute value. So that's k equals n plus 1 to little m. Again, we have in the correct range, so now we can apply this inequality, ak less than or equal to bk. That's less than or equal to k equals n plus 1 m bk. Okay, so maybe I should just kind of note the reasons here. So each of these is because k, so this is because k is bigger than or equal to, or I guess I can just say, yeah, k is bigger than n and n is bigger than or equal to n2, which is bigger than or equal to capital N, right? So both of those inequalities apply. And then the bk, that is equal to, and again, this is equal to the absolute value of the sum from k equals n plus 1 to m of the bk. Again, because the b's are all just positive, and that is less than epsilon because of this inequality here, right? So the m and the n are bigger than or equal to n plus n1 because they're bigger than or equal to n2. Okay, so this one here is because our m and n, m is bigger than n, is bigger than or equal to n2, which is bigger than or equal to n1. Okay, so that proves the first point. All right, so just a little bit. This, if you want to prove it for this eventually, right, to just say that it's the proof is more straightforward if you assume that this holds true for all k. If you want to prove it just for the eventually, if these inequalities are true eventually, then it's just a little bit more finesse in the proof. But the basic idea is just the Koshi criterion, right? If the a's are less than or equal to the b's, then this partial b tail is dominating this partial a tail, and the partial b tail is less than epsilon, so the partial a tail will also be less than epsilon. And then for 2, of course, 2 is just the contrapositive of 1. So this just follows from 1 by contraposition. Okay, so that's straightforward. So now if we look again at the Koshi criterion for series, we have, in order to show that a series, so we're looking at a series, in order to say that this converges, we need to bound the partial tails of the series, right? So we want this thing to be less than epsilon. And so ultimately we want this to be less than epsilon. One way to make that less than epsilon is to first apply the triangle inequality, right? So we know that this thing is less than or equal to, so we have a absolute value of a sum that's less than or equal to the sum of the absolute values by the triangle inequality, and is standard induction argument, right? So your triangle inequality says that a plus b less than or equal to absolute value of a plus absolute value b. If you have n terms in here instead of 2, you just continually apply the triangle inequality, like n minus 1 times, and you get the more general triangle inequality that the absolute value of a sum is less than or equal to the sum of the absolute values. So if we want to bound this thing by epsilon, it suffices to bound this thing by epsilon. Okay, so it's not necessary, right? So bounding this thing is going to be stronger than bounding this thing in general, but it would suffice to bound that thing. So if we can make this guy less than epsilon, then we can make this sum less than epsilon. Okay, so this is called the test for absolute convergence. So if we can make this tail, right, so this sort of partial tail less than epsilon for any epsilon, what that means is that we can show convergence of the series of absolute values, right? So if we can always make a partial tail like this less than epsilon, essentially what we're doing by the Koshi criterion is saying that we can make this series here converge. Okay, so if this series converges, that happens if and only if these types of partial tails can be made arbitrarily small, for any epsilon. And if we can do that, then that automatically bounds the partial tails of the original series. Right, so this is what's called the test for the absolute convergence test. So one way to try to show this series converges is by looking at the series of the absolute values of the terms. So that is the next little test that we'll cover here. Okay, so a little informal argument we just gave translates to if the series of composed of the absolute values of the terms converges, then the original series must also converge. So the proof is, if we want to show this converges by the Koshi criterion, we need to show that for any epsilon greater than 0, blah, blah, blah. So let epsilon greater than 0 be given. Then there is an A, or is there, by the Koshi criterion, there is an N such that when M is bigger than n, little n, which is bigger than or equal to big N, that implies that the absolute value of all of these absolute values from n plus 1 to m, which of course is just equal to the sum of the absolute values. We don't need that one on the outside. That is less than epsilon. But the absolute value of just the sum of the ordinary terms without the absolute values on the inside is less than or equal to the sum of the absolute values. So m bigger than n, bigger than or equal to n, capital N, implies that the partial tail of the original series is less than epsilon, which means that the original series converges by the Koshi criterion. So we kind of use the Koshi criterion twice. From the convergence of this, we have the, for given an epsilon, there is an n, blah, blah, blah. And then we show that given that epsilon, we can bound our original series, and so therefore by the Koshi criterion, we must have convergence. So we sort of took convergence of this, turned it into that for all epsilon type statement, and then from the for all epsilon type statement for our original series, we use the Koshi criterion in the other direction to say that our series converges. So this uses the if and only if. It uses both directions of the Koshi criterion here. Okay, and so this is a nice, this can be a nice test for convergence. So for example, something like, so as an example, you can take, say, the series -1 to the n plus 1 over n squared, n equals 1 to infinity. This must converge, so this converges by the absolute convergence test. Since if we take absolute values on the inside, we just get the 1 over n squared series, which we discussed the convergence of before. Okay, but you might want to note that the converse of the absolute convergence test is not true. So make a note here. The converse of the absolute convergence test is not true. So for example, we can consider the series of alternating 1 over n's. So they alternate in sign. This is called the alternating harmonic series. So this series converges, but of course, the series of just 1 over n's does not, but this diverges. Okay, so just because you know that a series converges doesn't mean that if you apply absolute values that converges. That's definitely not true. So this is called the alternating harmonic series here. Because it's just the harmonic series, but the terms are alternating in sign. And that's possibly, you remember that this series converges from calculus, and we haven't discussed the convergence of it in this course rigorously, but we can do so with the next test. So the next test, which is sort of standard from calculus, is that you have an alternating series test. So if you have a sequence of positive terms, and then you put them in a series so that they alternate sign, then that is always going to converge as long as the terms are going to zero. It's a necessary condition that the terms have to go to zero in order to have convergence, as we discussed above. And then as long as you make them alternate in sign, then that's always going to converge. So we have the next theorem, the next test from calculus that you'll recognize. So our alternating series test is that if we have a decreasing sequence which is going to zero, then if we form the alternating series from that sequence, then that must converge. And just a typical remark here is that we really don't need the sequence to be strictly decreasing. We only need it to be eventually decreasing. Okay, so it can kind of do whatever it wants for a finite number of terms as long as it eventually decreases, because we can take, right, so you have our series n from 1 to infinity. We can always write that as n from 1 to, say, capital N, right, where we can let the series do whatever it wants for those first big N terms, and then we can take the series from that point onwards, so from big N plus 1 to infinity, as long as the sequence is decreasing from here, right, then we can just apply this alternating, I meant to, there should be -1 to the n's here, so -1 to the n plus 1, and -1 to the n plus 1, -1 to the n plus 1. So as long as the ANs are decreasing from this point, we can apply the alternating series test to this series here, and then this converges, and this is just some finite number, right? Just some finite number of terms. We can always sum that up. So we could apply the alternating series test somewhat more broadly, as long as our series is eventually as long as the sequence of terms is eventually decreasing and going to zero. But anyway, let's take a look at a proof of this. So there are a number of proofs. Sort of the basic intuition for why the alternating series test should hold is that you have the first term in your, so the first partial sum is just the first term, right? So you have A1, then you're subtracting off A2, right? So you subtract off A2, and this is your A1 is equal to your first partial sum. You get your second partial sum by subtracting off A2, right? So this distance is A2, and that is less than A1, right? So you sort of have, so let's say 0 is over here. And then you're adding A3 to get your third partial sum, right? So the third partial sum is here, and this distance here is A3. So you haven't, since A3 is less than or equal to A2, you haven't gone back as far to A1. So you're sort of less than A1, but you're bigger than or equal to this S2. And then when you subtract off A4, A4 is less than or equal to A3, so you're not going to go quite back as far as S2, right? So S4 here is going to be, so that's S4, and this gap here is A4. Right, so you sort of just keep ping-ponging back and forth like this, and the odd partial sums form a decreasing sequence, and the even partial sums form an increasing sequence. And it's not too hard to argue. So one argument, you can use the monotone convergence theorem in order to produce to produce limits here. So you can produce a limit for the even partial sums and for the odd partial sums, and then you can show that those limits actually are equal to each other, and then argue that the partial sums in general must converge to that same limit. Also, you could make some kind of argument using the nested interval principle, sort of consider these, they're sort of nested intervals you can imagine in here, so you can make an argument related to that. And then the third argument, which is the one I'm going to give, is just based on, again, the Koshi criterion. Okay, but that's sort of the intuition for it, is just you have this back and forth kind of monotone sequences of even and odd partial sums converging in the middle. All right, so what we'll do is show that the partial sums form a Koshi sequence, so we'll apply the Koshi criterion. So we let epsilon greater than 0 be given. And what we'll do is, to sort of get an idea for how this is going to go, we're going to consider the difference. So suppose that m is bigger than n, and consider the difference of partial sums, and consider the difference of partial sums. Or well, I'll just say, and consider the quantity. So we'll look at the absolute value of Sm minus Sn. Right, that's just the absolute value of the sum from n equals, sorry, not n, k equals n plus 1 to m of -1 to the k plus 1, a sub k. And this is -1 to the n plus 2, a sub n plus 1, and then plus -1 to the n plus 3, a sub n plus 2, plus plus -1 to the m plus 1, a sub m. And what I can do is I just want to pull this -1. I want to make this first term be positive here. So I can pull out the -1 to that power, and by the absolute value, I'm just sort of going to cancel it out. So I'm just going to pull that out. And what I have here is, so if this one, so what we're going to have is -1 to the n plus 3 minus n plus 2, right? So that's just going to be -1. So actually this is just going to be negative an plus 2, right? And then the next one would be -1 to the n plus 4, right? But that differs from this -1 to the power by 2 powers of -1, which is just 1, right? So we're just going to get, in the next one, we're going to get plus an plus 3 plus. Right, so we're starting with this one positive, and then it's just going to alternate negative, positive, negative, positive. Whoops, so this should be a minus sign. Minus, ... and then finally plus, and we're going to have negative, we have m plus 1 minus n plus 2. So that is going to be, if we compute the difference there, we're going to have m plus n, or sorry, not m plus n, m minus n, minus 1, and then am. Now the first thing here is that this quantity is actually greater than, the quantity inside the absolute value here is actually greater than or equal to 0. And that's because of the decreasing terms here. So an plus 2 isn't quite as large as an plus 1. So when I subtract an plus 2 from an plus 1, this is still greater than 0, greater than or equal to 0, right? Then I add back this positive term, an plus 3. What I have is something that's at least as big as an plus 3, right? I had something that was non-negative plus an plus 3. Then I'm going to subtract off an plus 4, but that's not quite as big as an plus 3, so I'm still going to be positive, right? And this just keeps going down the line. So it's sort of straightforward induction proof shows that this is just equal to an plus 1 minus an plus 2 plus an plus 3 minus ... plus -1 to the m minus n minus 1 am. And the basic point here is that now I just want to say that this is less than or equal to a n plus 1. So maybe I'll put that here. So this is less than or equal to a n plus 1. Right? And again, that's just by induction, because when you subtract off this a n plus 2, of course, that's less than or equal to a n plus 1. Then when you add back the a n plus 3, that's not quite as much as you subtracted off before, right? So that's still going to be less than a n plus 1. Then you're going to subtract something off, that's going to be even less. You add something again, but it's less than what you subtracted off. So you're always going a little bit down and down every time, right? So every one of these pairs here, the minus and the plus, that's always going to be less than or equal to 0. Okay, so sort of both of these are by induction. So each step here. Right, these are just sort of straightforward induction arguments, so by induction. Okay, so the difference in these partial sums is always less than or equal to the first term in this partial tail here. But then you can kind of see where the proof is going, because we know that these terms themselves are going to 0. So I can make the ANs arbitrarily small. So that means that I can make the difference between these tails arbitrarily small. And that means that we can establish that the Koshi criterion holds for this series, and therefore it converges. So where we go from here, we just say since AK goes to 0, there is an n such that when k is bigger than or equal to that n, we have, so that implies that the AK in absolute value, right? So the absolute value of AK, our AKs are positive, so this is just AK, is less than epsilon. But then, right, just from this sort of computation up here, but then if m is bigger than n is bigger than the same capital N, we find that the absolute value of Sm minus Sn, that is less than or equal to a n plus 1, and this little n plus 1, that's bigger than this little n, right, which is bigger than or equal to the big N. And so therefore, right, so k, so little n plus 1 is one of these k's, right? So that means the AK is less than epsilon. So that's less than epsilon, and so by the Koshi criterion, our series converges. So the series sum of the negative k plus 1 AK converges by the Koshi criterion. Okay, so that's one proof of the alternating series test using the Koshi criterion. So just taking a second to reflect on these tests, we have the alternating series test, and we have the absolute convergence test, and we have the comparison test. These are all results from calculus that you probably had some reasonable sense of their truth, and sort of had an intuitive idea of why they were true. High degree of confidence that we understood the reasons for why they were true. But you really realize that when you're looking at the proofs here, that the proof in all of these comes down to the Koshi criterion, because for example, in this comparison test, you might have this series of BK, of the BK terms that converges. You might actually know the exact sum of this, right? But you want to you want to deduce from that the sum of the AK series, and you might not know how to precisely sum this series, right? So you need to know that there is a limit of the partial sums of this series, and knowing that partial sum is out there really comes from the completeness of the real numbers, right? So even though there's this sort of strong intuitive sense of the convergence of the BK series implying the convergence of the AK series, you can't really strictly, logically deduce the convergence of the AK series unless you know something about the real numbers, right? Something related to the completeness of the real numbers. And the same is true of the absolute convergence test and also of the alternating series test. So even though our sort of intuition of these results and why they're true doesn't change from calculus to here, what has improved is our logical understanding of the situation. So the convergence of these series, what we really needed to know to get to the bottom of those results is we needed to articulate exactly what it is that we're talking about when we talk about the real numbers. The nature of the real numbers and the completeness of the real numbers was the key issue. So hopefully you can appreciate the value of that clarification, even if it doesn't really, it doesn't, for me, it doesn't deepen, my intuitive feeling for why the alternating series test is true, but it does clarify the issue logically, that in all these series tests, the issue that has to be grappled with is the nature of the real numbers themselves. So that in itself is, I think, an achievement and accomplishment worth sort of reflecting on. This last topic I want to touch on is is the topic of rearrangements. It's something you probably didn't see much in calculus, so I give you something in this lecture that's a little bit new, possibly. So the topic is the following. So if you consider the alternating harmonic series, right, we have one, we have minus 1/2, we have a third, we have minus a fourth, a fifth, minus a sixth, goes on like this, right? So these are all the terms we're summing in the alternating harmonic series. So let me see. So we'll say plus, plus, minus. So whatever the alternating harmonic series comes to, we'll call that the sum S. And you might remember from calculus, actually this converges to the natural logarithm of 2, but that's neither here nor there for this discussion. Now, if we look at 1/2 S, right, we can just, by our result about multiplying a series by a constant, we can just distribute that constant. So we get 1/2 minus 1/4, 1/6, minus 1/8, 1/10, etc. Right? But you might notice here that 1/2 and minus 1/2 sort of match up here. And minus 1/4, minus 1/4 match up here. 1/6 and minus 1/6, they match up here. And so what I can do, maybe it'd be better to line things up then to make this match. So this 1/2 S, that's going to be, so we have 1/2, then we have minus 1/4, and then we have plus 1/6, and then we have minus 1/8, which is going to match up with, excuse me. So let's walk this out a little further. Minus 1/10 plus 1/9, or sorry, minus 1/8 plus 1/9 minus 1/10, and then we'll have plus 1/10 here, plus dot dot dot, minus dot dot dot. And so if we sum these two together, we get 3/2 S. That's going to be equal to, we have 1, and then these cancel. So we just get a plus 1/3. Then we have minus 1/2 plus 1/5. this cancels. Then we have plus 1/7 minus 1/4 plus 1/9, a cancellation. And then we would have a, looks like a plus 1/11, and then we would have a minus 1/12 up here, right? Minus, and then plus 1/11 minus 1/12, and we would have, we're alternating, we'd have another minus 1/12, and that would give us a minus 1/6. And so what you kind of notice here is that this 3/2 s, right? So the sum of these two is 3/2 of whatever this original s sum was. But in fact, this s, this 3/2 s sum, if we sort of write it more compactly, it's 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6. What's happening here is we're taking positive terms, so we're taking two positive terms and then a negative term, right? So the first two positive terms are 1 1/3, then we take the first negative term, then we take the next two positive terms after those, and then we take the next negative term after that one. Then we take the next two positive terms available, then the next negative one after the first two, and we keep going along in this fashion. And if we do this, the argument we just gave suggests that that the sum here is actually different than our original sum s, even though every term in this s sum is represented here, right? So eventually, right, we cover exactly, each one of the summands here with the correct plus and minus is exactly one of these summands in the original s sum, but we come out to a different value, right? We actually come out to a larger value. And so the reason for this is because, well, we're really considering a different sequence here, right? When we're talking about this sum, we're talking about the sequence of partial sums. But of course, the sequence of partial sums for this series is different than the sequence of partial sums for this series, because we're using two positive terms first before we put in any negative terms. So, intuitively, it's not all that unreasonable to think maybe this sum comes out to be larger because you're putting the positive terms, you're taking more of them before you take a negative term. So each of the partial sums of this is going to be bigger than the partial sum of this, and so maybe not all that unreasonable that it comes out to a different sum, and one that's larger. And so this is called this series here is a rearrangement of this first series. So you just take the same summands just in a different order. And so the alternating harmonic series is what's called conditionally convergent. So it's a series which is not absolutely convergent. And so the conditional convergence means sort of that what it sums to depends on which order you take the summands in. So we would say that S is conditionally convergent. Conditionally convergent. And the definition of conditionally convergent is just that it's not absolutely convergent. So i.e. not absolutely convergent. And in fact, if you take any series which is not absolutely convergent, then if you take the sums, if you take the terms in a different order, you can make it converge to different things. And so the theorem that we're going to prove here is for the other case. So we're not going to study the conditionally convergent case. What we're going to show is that in the case of absolute convergence, and so absolutely convergent, I guess maybe I should have sort of defined that. So absolutely convergent, what that means is that the sum of the absolute values converges. So the definition is that a series is absolutely convergent if the sum of the absolute values converges. So the sum of absolute values converges. That exactly means that your original series, let's say the original series, is absolutely convergent. Okay, so the opposite of absolutely convergent is conditionally convergent. And the intuitive meaning of this is that if your series is conditionally convergent, you can make it converge to different values by taking the terms in a different order. And what we're going to show with absolutely convergent is that this absolute, well, sort of refers to the absolute value here in the definition of absolute convergence, but also what it really means is that no matter how you rearrange the terms, you're always going to converge to the same sum. So that's the theorem that we'll end on here. Okay, so precisely here, if you have an absolutely convergent series, that is one for which the sum of the absolute values of the terms converges, then any rearrangement of your series converges to the same value as the series itself. And just to clarify what a rearrangement is, intuitively you're just taking the A's and you're swapping them around, and then taking the partial sums in that order. But to make this precise, the swapping around of terms, right, that just corresponds to a bijection from the natural numbers to itself. Right, so you're just moving around the indices that label the A's and taking them in a different order. So taking them in a different order, that just corresponds to a bijection. So your BK series is a rearrangement of the AK series if B sub k is A sub f of k for some bijective function from the naturals to itself. Right, so the second term of the B series might be the fifth term of the A series, and the 100th term might be the 1000th term of the A series, depending on how you're swapping around. But basically, you're just so you're just using this bijective function to take all of the A's in a different order. Okay, that's the basic idea. All right, so to start here, we'll let the sum of our original series be equal to A. And then what we have to do is show that this rearrangement converges to A as well. So ultimately what we're going to be concerned with is making the partial sum from k equals 1 to m of bk be close to this A. So I like to try to visualize the situation to get some handle on what the proof should be. So sort of visualize, like we have our A terms here. So we have A1, A2, and etc. So we have a bunch of A's here. And our B's, so we have this rearrangement, right? So you might have, your B1 might be here, and then you have B2, and you have B3, and you have B4, etc., B5, B6, whatever, and you want to take enough of these B's, right, so that you know that you're sufficiently close to A. And what is A? Well, A is what you get, right, you get very close to A. So A is what you get when you sum up an infinite number of these A's, so to speak. But we can get arbitrarily close to A by taking sufficiently many of these A's. Right, so we know that, like, if we take a large number of these A's, say A from starting there out to there, that we're going to be very close to A. Right, so this is going to be so if I can, let me see. Just need another color here. Right, so if we take a large number of A's of the ANs and sum them together, this is going to be close to the limit value A. So let's say this A here, let's say that's A sub n. Then what I want to do intuitively is I want to take enough terms in this B series so that I fill out all of the A's, right? So all of the A's from A1 to A big N are represented by B's. And then I'm probably going to have a lot of extra B's, right? I mean, because just going up to B sub big N isn't going to work because I could be taking B's, out here. This bijection might have rearranged things so that I'm taking some B's out here before I get around to taking the ones here. But I know that this rearrangement, right, it's defined by a bijection. So there's got to be, right, so I have to cover all of these A's at some point, right? So there's definitely some point I can go out, take the B's, and I'm going to cover all of these A's here. So if I go out to that point, right, so I need to go out to some, to like B sub big N1 or something, big enough so that all of the ANs here are covered. So we can conceptualize this. So let's try to do simulate a computation here. So if we sum from k equals 1 to m, the bk's where this little m is past the point where all of the where the b's are covering a1 through a big N, right? Then we have this. Well, I know that this sum of b's, that's covering the sum of the a's from 1 to big N. And so I have ak, and I know that that's close to a, right? So I sort of want to group that with a, and then I have a bunch of extraneous stuff. So then I have some bk's, and, well, I just sort of say miscellaneous. I don't know, the k are these miscellaneous extra ones which fall outside of this, where the k is bigger than n. And so, ultimately what I want to do is I want to show that this is arbitrarily small. So I can kind of split using the triangle inequality. Right? So I know that I'm going to be able to make this difference arbitrarily small because my original series is converging to A. So I'll be able to make this less than epsilon over 2. And then I have this miscellaneous stuff here. And so I have sort of the absolute value of these miscellaneous B's. But all of those B's are falling in a tail after this A endpoint, right? And I can control the sum of the absolute value of those A's, right, in a tail, because I know that the sequence of the series where you take the sum of the absolute values converges, right? So I can control any partial tail of that series. So this thing here is less than or equal to the sum, right, of the BKs. I can just take this from really it's going to be AKs, right? All these BKs are going to be AKs, and I can go, it'll be from K equals big N plus 1 up to whatever. Doesn't even really matter. Just sort of put a question mark there. So AK with the absolute value on it, and I know I can make that less than whatever I want just because the associated series is converging. So I can make this tail, right? As long as I take this n far enough out, I'm going to be able to make this tail small. And then the sum of those epsilon over 2's is going to be epsilon. So I can control everything here. As long as I'm far enough out, I'll cover enough A's to get close to this A. And simultaneously, if I'm far out, then all of the rest of this stuff is just getting arbitrarily small, right? Just getting smaller and smaller. And so I can make this total thing less than epsilon. And so that's sort of the outline of the proof. And then you just have to figure out how to actually say all of that so that it's precise. So first, so we have that, and let's say epsilon greater than 0. So let that and epsilon greater than 0 be given. Okay, so now since we have this series converging, so there is an N1 and N1 such that the difference between the sum from K equals 1 to N1 of the AKs minus A in absolute value is less than epsilon over 2. Okay, so my picture here, this N, I'm just going to call that N1. Okay, so we know that that is going to be less than epsilon over 2. Now, also we know that we want to be going out far enough here so that the tail of the absolute value series is less than epsilon over 2. So there is also, so by the absolute convergence, there is N2 such that when M is bigger than N is bigger than or equal to that N2, that implies that the sum of the a's, so ak, from k equals n plus 1 to m, that is less than epsilon over 2 as well. And now that we have those two, this n we were talking about here, we really want that to be the maximum of these n1 and n2. So because this n here, we sort of applied, we applied, so we applied this epsilon over 2 and epsilon over 2. That was conditional on this n. And we want our n, right, to be big enough to apply this and also to apply this. And so that means we need that n to be bigger than or equal to the n1 and n2. So set n3 equal to the max of n1 and n2. Okay, so we have this picture here. There's our n3. And now what we want to do is take enough b terms so that we cover all of those first n3a terms. Right, and so that is going to use the fact that our function is a bijection. So what we can do is, so we want to know sort of how many of the b's do we have to take before the set 1 through n3 is covered by the bijection f, right? And so what we can do is just take the inverse image of the set 1 through n3 by the bijection f. So what we're going to do is we're going to let capital N equal the max of the set. So this is the max of the set f inverse of the first n3 integers. Okay, so this is my notation for the first n3 natural numbers, not integers, natural numbers. First n3 natural numbers, and then we take the inverse image by this f. So that is, we look at all of the natural numbers that map into this set from 1 to n3 and look at the biggest one of those. So in terms of this this picture down here, we're just looking at this big N here is just saying how many of these B's do we have to take before the first N3 A's are covered, right? So so look at this picture. We have B1, 2, 3, 4, 5, 6. Maybe like B7 and B8 are out here somewhere, and then we have B9, B10, B11, maybe B12 is out here somewhere, B13. We keep going like this, and we're just keeping track of which one of the, which of the B's are covering the A's. That's this F inverse of N3 set, right? We're just seeing which indices are mapping into the first, first N3 of the A's, right? So you're just saying, so the first 1 through N3, right, that's represented by this A1 through AN3. And then the F inverse is just seeing which B's, right, so which indices with the B's are mapping into there. And we're just seeing what's the biggest one. So how many of these B's do we have to take before all of these A's are filled out? Okay, so in this picture, this F inverse of N3 set, right, we'd have all of these numbers, B1, B2. We wouldn't have B3, that falls outside here. We'd have B4, B5, and B6, but we wouldn't have B7 or B8. Right, and we just sort of keep track of this until every single one of these A's are covered. And once we've covered all of the first N3 A's, we can stop. And so that's our capital N point. Okay, so that's how many of the B's I need to take before I'm sure that I've covered all of the A's. That's what's going on. So if we have this capital N is the maximum of this set, what that says, so we have let n equals that, so that this set then, F inverse of N3, if capital N is the biggest element of that set, then that means that that must be contained in the set of the first n natural numbers. i.e. the set of the first n3 natural numbers is contained in the set f of the first capital N natural numbers. And now we're ready to show that if we take a b sub n, little n, where little n is bigger than this big N, then the partial sum up to of the b's up to that little n is within epsilon of a. So let me erase this stuff first. So thus, if little n is bigger than or equal to big N, we have the distance between this partial sum and A. What we can do is, this is the sum of the bk's where k is in the first n natural numbers. And bk, that's a of f of k, by definition. And if the k's are in the first n natural numbers, then the f of k's are in f of the first n natural numbers, right? So this is the sum. So we're summing all of the a's, so let's say a sub m, where m is in f of the first n natural numbers in that set. But f of the first n little n natural numbers, that must contain, right, the first little n natural numbers contains the first big N natural numbers, and so f of the first n little n natural numbers contains f of the first big N natural numbers, and that contains n3, the first n3 natural numbers. So what we can say is this is the sum from, say m equals 1 to n3 of the AMs. We want to group that with A, because we know that's going to be, so this partial sum of the A's is going to be close to A. And then we'll have all of the other stuff. So then plus the sum over M in this set, f of n, but then minus the first n3 natural numbers. And this we did because the set of the first n3 natural numbers is contained in this. So the reason for this is that we have that the first n3 natural numbers is contained in f of the first big N natural numbers, which is contained in f of little n. And so that is less than or equal to the difference here, m equals 1 to n3 of the AMs minus A, plus, and so it's less than or equal to the absolute value of this sum, and then that's less than or equal to the sum of the absolute values. So this is less than or equal to the sum of the absolute values of the AMs, where m is in f of n minus the first n3 natural numbers. And then that is less than or equal to, so we just have, so we have this m from 1 to, well, actually, I guess we can say, since n3, right, is bigger than or equal to n1, this first thing is less than epsilon over 2. Right, so this is because, so n3 is bigger than or equal to n2, or n1. Okay, so we're far enough out that that partial sum is close to A. And then this next term, we can just make this, so this might be, right, so this set might not be a sequential set of natural numbers. This might be some kind of, because this bijection f might be throwing things around quite a bit. But what we can do is take this to be from n3 plus 1 to, we can just add in extra terms, right? So if there are sort of gaps here, it's not sequential, we can just throw them in, right? Because we're only adding, we're only increasing the sum, so that's fine. And so we have the AMs, and then this would go up to the max of whatever the f of little n set is there. But then this m here, the n3 plus 1, that is going to be bigger than or equal to n2, right? So this is bigger than or equal to, so then n3 plus 1, that's bigger than or equal to n2, and so we're past the point at which all of the, right, so this sort of partial tail sum is less than epsilon over 2, right, whenever we're summing past that n2 point. So this then is going to be less than epsilon over 2, and that equals epsilon. Okay, so that successfully bounds the difference between the bk partial sum and that limit a, and so therefore that the bk partial sum must be limiting to that same value as the ak series. Okay, so that just brings me to 1 hour and 20 minutes, so that will be enough for this lecture, and that concludes chapter 2 in the text.